Welcome to this little webinar about TMAs and uplink performance and modern systems in general. In the modern systems, we have a situation that is very sensitive to uplink performance. We have MIMO that requires high CORI to get a high rank for our UIs and the communication. 5G in general with the new modulation in uplink that is less efficient than 4G. We have carrier aggregation where uplink have to support two uplink downlinks instead of only one. And we always need to look at the frequency efficiency. Same thing with TDD, but even more. In TDD, everything we do will also affect the available time for the downlink, which means general performance. So a fact that needs to be considered is with no uplink, we actually have zero downlink. And today we will try to answer the question on how much uplink do we need before we get degradation of the downlink. In general, we will see that 300 kilobits and more, that is what is required to provide a downlink with no uplink limitations. To improve the uplink in general, to get it to perform better, basically doubling the performance of the uplink, the TMA is a very good device. We must also remember that we have two things, basically three things that degrades the uplink. Interference, that is all in the operator's hands. Thermal noise, that will be solved by TMAs. And passive intermodulation, that can severely degrade the uplink. That is solved by using good equipment and doing good installations. In every system, we actually need to talk about balance. From the old voice days, it was quite easy because we had the same service, uplink and downlink, but we actually need to look at balance also in the modern systems. What we mean with balance is the ability for the uplink to support the same coverage area as the downlink. In general, we have an area that is affected by interference from the downlink that is significantly larger than the area that is actually supported by the uplink. So that's why I call the blue area here the revenue generating area. And the revenue generating area is with the area where you have good or at least decent KPIs. The gray area outside here is covered by the downlink, which means that the UIs will try to do setup attempts, try to run with full TX power in order to connect. But the KPIs will always be very bad. So it will not bring in much revenues. If we, with the TMA, improve the uplink, note that first of all, the downlink area is the same. We do not extend the downlink coverage area. That is a misconception. What we do is we extend the area within the downlink coverage that provides good KPIs, high quality communication, and nice revenues. So what is happening is that the revenue area is increased by the TMAs. The numbers you can see here is straight from a trial recently done in Southeast Asia, where we can see the range. The average distance to UE did grow by 24%, which means 53% more coverage area for the uplink or for the UEs. Doing a link budget or a balance calculation can be done in several ways. This is going to maybe the most renowned or admired persons, Harry Holma and Antti Toskala from the Blue Book, a book that I strongly recommend. In their book, they have this link budget calculation that is very interesting because it's, first of all, GSM, 12.2 kilobits, HSPA, 1 megabit, and LTE, 1 megabit. And here we can see that they are using 2 dB feeder loss or jumper loss, I would say. This corresponds to, depending on frequency, it depends on the length of the jumper, of course, but on 1800 to 2.1, this is roughly a 6-meter jumper or 5-meter jumper. We can also see that the link budget for the downlink here allows you to have 163.4 or 0.5 dB of path loss maximum. And I always, in my mind, thought that GSM was a better system for general coverage. But we can see here that both AGSPA and LTE actually provide longer coverage, 2 dB more coverage area than the old GSM. So they're pretty good. If we now look at the uplink, Harry Holman and Titoskala use 64 kilobits for this balance calculation. And as we know, or as we will see, 64 kilobits is by far too slow to support the 1 megabit of the downlink. This is only 6%, and rule of thumb typically say 15% of the downlink is what you need in uplink. So even though we start off with a very, very slow uplink, and we can see here that they use TMAs, because cable loss in uplink is set to 0 dB, and that's typically what you do when you use a TMA. We can also see that with 2 dB feeder loss, we only have 2 dB of a noise figure in the base station. The RU itself typically have around 3 dB or 2.8 to 3 dB in noise figure. And we have, as you can see, gained almost 1 dB in sensitivity, even though we have 2 dB of feed loss, which is the typical situation with a TMA. So with the 3 dB roughly of improvement from a TMA, the uplink at 64 kilobits is still 2 dB short on AGSPA and barely reaches balance on LTE. This is quite interesting to see that they match with 64 kilobits a 1 megabit downlink with the TMA. If we would switch off the TMA, we will lose about 3 dB, which means that LTE would support 32 kilobits. AGSPA, that is already 2 dB short, will go down to roughly 16 kilobits, where the downlink still provides 1 meg. So that is what we mean with the revenue generating area is significantly smaller. This was calculations, theoretical calculations from the book. If we now look at a simulation done by Nokia in the Nokia simulation tool, we can see that they have been very careful not to overstate the enhancement that the TMAs give. So here we have 2 dB of jumper loss in downlink and 2.25 with the TMA in downlink. That is because of the short jumper between the TMA and the antenna that is added when you use a TMA. 0.25 dB is maybe slightly high because it's a very short jumper. They also use 0.5 dB of downlink loss in the TMA, which is definitely on the high side. That is for some TMAs in the corner frequency. The general loss is more like 0.2 dB. So this simulation is by no means a over-optimistic simulation. In this situation anyway, we use 5 megabit of downlink speed, and the left columns, those values, the 2 left columns, represent no TMA. The right hand 2 columns represent the system with a TMA. In both cases, we have 5 meg as the downlink speed. But in the situation with no TMA, we assume 100 kilobits of downlink speed. With TMA, we assume to get, or we choose to simulate with 200 kilobits in uplink speed. Looking now at the same kind of link budget as from the blue book, we can see that maximum allowable path loss for downlink with no TMAs and only 2 dB jumper loss is basically 160 dB. Maximum path loss in uplink for 100 kilobits is 156 dB. So we are 4 dB short of providing 100 kilobits in this balance calculation. With TMAs, we have now lost almost 1 dB in downlink due to the added jumper and the 0.5 dB of TMA loss. But with 200 kilobits and the TMA, we still have exactly the same path, allowable path loss in uplink. So with this situation with the TMA, we still have 3 dB of overpower, so to say, with 5 meg in downlink, so with 5 meg of data rate. So the 5 meg downlink is still 3 dB stronger or higher in performance than the 200 kilobits with the TMA. So looking at the balance situation, the TMA have here doubled the performance of the uplink. Below, we can see, if we want to see it in numbers of base stations needed, number of sites, or ranges, etc. And we can see that the uplink with the TMA at twice the data rate is actually 10 meters longer than without the TMA. If we now use a 1 dB jumper, which is where most people would say that we have an RU and that is a feederless site. 1 dB is not feederless. 1 dB is significantly more than 0. So there are really no completely feederless sites. But in our recommendations, we typically say that below 1 dB then it's hard to justify the TMA. And with 1 dB and up, that's where you should consider a TMA. So this is the result we get with 1 dB jumper loss. Same as before, 1 dB in no TMA downlink, 1.25 dB with TMA downlink due to the added short jumper. Same loss is set in downlink for the TMA, half a dB, and 0 with no TMA. In the no TMA situation, we still have 5 meg and 100 kilobits in uplink. And that gives us still 100 is slightly different environmental here, but 161 dB roughly for the downlink to achieve 5 meg and 157 dB maximum path loss to provide 100 kilobits. With the TMA and only 1 dB of path loss, not that, we still have 5 meg and 160 dB of maximum path loss. And now in uplink, 157 dB with 165 kilobits per second. That is 65% up, but okay, we're a few tenths of a dB short, so 60% up in speed for the uplink in performance from just 1 dB of path loss. And we can still see here that the difference in coverage with 60% higher data rate is within a few meters, the same as no TMA. This is still simulations, so it's not the real live situation. Here on the slide after this one, I will show you from a real case. Now, what is this slide trying to represent? Well, it's a behavioral description on how the end user reacts to delay in your network. If you can provide a response of fractions of a second, the user will feel that wonderful feeling of direct response, a very snappy network. When you pass 1 second, they're still quite happy, but they start to feel that the system is slightly delaying their actions. At 10 seconds, most of the users actually give up because they are at the mercy of the computer and they are very unlikely to return to this application or web page. So the general concept is that 2 to 3 or even 4 seconds is the maximum delay we can provide for a user and still maintain the user to stick to the application. In the important question that we have been touching a few times now, the question on how much uplink do I need? As the downlink is where we measure, but how much uplink do I need to provide the service for the downlink? This is a slide done by Ericsson from their mobility report. In the center here, we have 5 megabit of uplink and 20 megabits of downlink. Going this direction, we slow down the downlink, but we maintain the speed of the uplink. Going the other way, we slow down the uplink, but we maintain the 20 meg in downlink. And all those colorful things we see here, each color represents one application. And the applications are price runner, banking apps, Facebook, and the most common applications that we as end users tend to use. And the dotted red line here corresponds to 4 seconds of delay. That's where we know that the user starts to be a bit frustrated. And with full speed in both links, of course, the system is very quick, and we sit in general with 3 seconds in delay. Moving to the right, we can see a fairly linear increase of delay, which should be quite expected. We go from 20 megs to 5 meg in uplink, and we start to see, 5 meg in downlink. 5 meg downlink and 5 meg uplink. We can see that the delay have increased slightly, reducing the downlink now to 3 megabits, and we can see how a few applications start to breach the 4-second line, and all the others start to be slower. 2 megabits, a few more applications breach 4 seconds, some of them still stay in acceptable performance. At 1 meg, all applications start to breach the 4 seconds, and some of them are way up to approaching 10 seconds, which is where everyone will drop the application. And no, we still have 5 meg of uplink performance. Going the other way is quite interesting. Going from 5 meg uplink to 1 meg uplink, we can see that the delay is almost unchanged. So obviously 1 meg in uplink is easily enough. It's good enough for the to serve the downlink. Stepping down to 300 kilobits, now we see how most of the applications are moving closer to the 4-second line, but they're still on the right side of it. So 300 kilobits can here obviously be seen as fast enough to support the most of the speeds in downlink. We can see that it roughly now with 20 megabits available in downlink, it performs roughly like somewhere in between 20 and 5 megabits. It starts to be slightly hurt. If we now slow down to 150 kilobits, remember, still having 20 megabits of downlink performance, but only 150 kilobits in uplink, we can see that 5 of those applications breach 4-second line, and all the others are approaching the unacceptable limits. So 150 kilobits, well, for some applications, we can say that it's enough, but for most applications, it starts to affect our downlink performance. Going down to 75 kilobits, we can see that every single application is way outside of acceptable performance. And this is, to repeat myself, still with 20 megabits available in downlink. You only provide less than 1 megabit of downlink performance due to uplink delays and uplink's limitations. And remember now, the simulations we saw before. Harry Holman at Toscala simulation said 64 kilobits with the TMA, 32 kilobits without. That is somewhere down here in 20 seconds in total delay. The simulations down by Nokia was for 100 kilobits, which is not enough, but almost. And with the TMA, we did step up to 160, which is pretty good, or 300 kilobits, 200 kilobits, sorry, which is all the applications stay below the line. So I think this slide answers the question, how much uplink do we need? More than 0, and typically I would say 150 to 300 kilobits is what we need to provide a decent functionality from our downlink. Now, that was still theory, and now an example from Asia, an installation and live performance. This is done with RUs, Nokia RUs moved down to ground level for serviceability and the reasons of a weak tower. The objective was to improve uplink coverage, improve network quality, that is mainly the KPIs, and increase the uplink scenario to be able to grow traffic. The KPI summary from this trial shows that the scenario was up 3.4 dB, and the jumper loss or feeder loss was about 2.5 dB, and that illuminates our typical rule of thumb that it's feeder loss plus 1 dB. That is the general gain with the TMA, because system sensitivity typically goes down to about 1.7 dB of noise figure with the TMA, and it's in general it's 2.8, 2.9 dB without the TMA. Uplink traffic was increased by 11% and uplink throughput by 11%. Normally when you see 11% more traffic, you see around 11% slower speed. Here we increase both speed and data volume. Uplink throughput, MCS, that's modulation coding scheme in uplink, did go up 2.4 steps. 2.4 steps in MCS is roughly 26% higher spectrum efficiency. And spectrum efficiency is extremely important because the most expensive device in every sector is the spectrum. If you look at the total cost, total investment per sector, it is the license that dominates. A rule of thumb that is not exact, but a rough estimate is $1,000 per megahertz per sector. So if you have 10 megahertz in spectrum in your sector, which is very low, it is still $10,000 in license cost for that sector. So spectrum efficiency is very, very important. And here we increase the spectrum efficiency by 26%. The uplink coverage area, or the revenue generating area, was extended by 53%. That is a lot. 53% larger area with good KPIs, and still with the same downlink coverage area. Downlink traffic, remember the only thing we have added here is one extra jumper and a slight loss in the TMA. Still, downlink traffic has increased by 28% and also the throughput by 28%. This is normally contradictory, so we have improved the downlink performance with much more than 28%. If we now look at the quality figures, the drop ratio, ERAB drops down 71%, radio bearer drop ratio 73%, CS fallback, how well do you maintain your traffic on 4G instead of falling back to 3G? 22% less fallback. 58% less redirection without CS fallback. Average latency in uplink is down 11%. Even though we have 11% higher, more traffic, latency is still down 11%, which corresponds to, of course, the uplink throughput that is 11% higher. So all in all, the KPI improvement from such a tiny and simple and easy to handle device as a TMA is quite impressive. So TMAs of today. TMAs are only for ground-based base stations, but I would say this is a very common sight today due to weak towers, or that this area is so valuable, so it's better to put antennas here than RUs. It is also due to serviceability. If you have your RUs sitting up here behind the antennas, very close to the antennas, you have to switch off all the 15 systems to service only one RU. If you have the RUs a little bit below the antennas, you can do a hot swap of one RU and leaving the other 14 systems up and running. That's a huge benefit. So a lot of operators today see the benefits of moving the RUs a bit down the tower. It could be tower load, serviceability, site sharing, doing it with another operator, or regulations. That is the beauty parlor. I mean, we have to have invisible sites and things like that, and it's easy to move down the RUs. And in a site like this, of course, we do not have a zero jumper loss. Even in a site like this, we could say zero jump loss to this RU that sits just behind the antenna. But when we move down to those RUs, it is not a zero jumper loss up to the antennas. So typical jumper loss we can see here, and if we add the additional 0.1 dB for the connectors, we can see that 1 dB happens quite early. It's around 3 meters here with the jumper loss, with the connector loss, 3 meters for 1800, and 5 meters for 3.5. So going through the theory behind it, we could use Freeze formula, but formulas are hard to digest and not very fun to present in a slideshow. So this is a graphical presentation of Freeze formula. This picture here describes the spectrum straight from the UE, only attenuated by path loss. So it will start to approach the thermal noise floor, the KTB noise, and we can see that we still have quite a significant C over I, because now the interference here is noise and this is the signal. C over I is this distance. When we run over the cable, we get a loss, which means that the signal, the carrier, is attenuated. The thermal noise stays the same. We still have a decent C over I that could be used, but when we add the 2.8 dB or 3 dB noise figure of the base station, we can notice as this is now the remaining C over I, and that is not okay for a communication with the 150 to 300 kilobits that we know that we need. If we now do the same graphical description, but now with the TMA, we have the same here, the same C over I entering the antenna, going straight to the TMA with a minimum of loss in that first little jumper. We now see that we have almost the full C over I in the air entering the TMA. And this is amplified. This is the amplified noise, and this is the amplified carrier. So now C over I is set by the amplified noise and the signal. When this composite signal passes through the cable, both the amplified noise and the carrier are attenuated. It's only thermal noise floor that is not attenuated, Amplified noise is a man-made thing, and it is attenuated in the jumper. When this enters the base station, we have a separation here of roughly 10 dB. The amplified noise is roughly 10 dB stronger than the input noise of the RU. So adding something that is 10 dB lower means that we add 0.4 to this. So we get 10 log 1.4, and that is, sorry, 10 log 1.1, and that is plus 0.4 dB. So instead of having the 1.7 1.3 dB of noise figure of the TMA, we now get 1.3 plus 0.4 and about 1.7 dB of system noise figure. And we have almost the same C over I as we had in the antenna. We have lost a marginal amount of C over I. That is how TMA works. Pretty simple and very, very reliable. Most of you listeners, I guess, have worked with TMAs in the early days with GSM, etc. And remember TMAs as single band devices, one per system. Sorry, one or two per system. Today, almost every TMA is multiband. We still have the single band, and they are very small and with main and diversity channels. So in a way, they are also double, but most of them are dual band. And the dual bands you can get in many fashions. For example, if you want to have, like here, you have two connectors down, two connectors up for 2 or 3 bands. This is very nice for an ultra wideband antenna from 1710 up to 2700. You can run 2G GSM, you can run 2100, you can run LTE, or even 5G on this broadband TMA or multiband TMA. You could also get it with 4 connectors down and 2 connectors up. If you want to have 2 RUs in your tower, one for LTE and one for GSM, well, you have the 4 connectors, and this is an active diplexer, so to say. You have the same box count as without the TMA, but you get the TMA functionality. So this is a high performance diplexer with ultra low system noise figure. You can also get a triple band TMA with, in this case, 2 connectors down and 4 connectors up. So whatever configuration, I would be surprised if microdata cannot support you a multi-band TMA that will fit your purpose. So uplink challenges in 5G. Why is uplink a challenge in 5G? Well, first of all, it's very similar to 4G. Most of the things in 5G, in the RF part, is similar to 4G. But we now have OFDMA also in uplink, which means that the linearity requirements on the transmitter in the UE is much higher. That means that the efficiency in the UE transmitter is lower. And that actually means that having excessive noise in your uplink and overcoming that noise, fighting that noise with UETX power is now much more expensive, so to say. So 5G benefits more than 4G and more than 3G from having a low noise, low interference uplink. This means that both PIM and thermal noise must be minimized in 5G to provide a decent UE battery lifetime. And here we can see the coverage situation on different frequencies in 5G, and we can see all of them sacrifice the uplink. We have a much weaker uplink than downlink. And looking at 3.5, we can see that even the 1800 uplink is weaker than the 3.5 downlink. So the 1800 uplink really would benefit a lot from the typical 3 dB improvement that you get from a TMA. Then you get more or less a link budget balance between 1800 and 3.5. So this is, by the way, a slide from Nokia. So again, RUs are typically not feederless. They are not having a zero feeder loss. We have 1 dB of loss typically at 3 meter for 3500 and 5 meter for 1800. So how can we improve the uplink of 5G? Well, we have massive MIMO, a very advanced system that improves both uplink and downlink. A very expensive system, at least for the moment, mainly adaptive, suitable for smaller cells in urban areas. We can, of course, make smaller cells. In a smaller cell, we typically have uplink performance enough all the way out. We could, of course, do decoupling of the uplink. That means we move the uplink down to a lower frequency and maintain the downlink on a higher frequency where we have capacity. And of course, we do have the dilemma then that the path loss and the propagation is different for the higher and the lower frequency. And we can also use a TMA. And especially if you look at TDD, in TDD, any degradation of the uplink will have to be compensated for by using more time for the uplink. That time is removed from the potential downlink time, which means that uplink now in a one-to-one fashion affects the performance in downlink. So for TDD, TMAs will be extremely beneficial, actually more than FDD. But of course, a TDD TMA is fairly complicated, much more complicated than FDD. But I do hope that we soon will present a very nice TDD TMA for you. So, as a summary, TMAs always improve the uplink C over I. There are basically no negative side effects from a TMA. If you apply TMA in a sector that is completely interference limited, the TMA will still not provide any negatives. If you look at the nighttime and indoor users, etc., they will still see a benefit from the TMA. TMAs are a viable solution when uplink limits the downlink performance, the drop call rate, or your general KPIs. And if you have a jumper loss of 1 dB or more than that. 5G networks definitely have an uplink challenge. I think that more and more of you listeners here start to realize that even before this webinar. So TMA supporting the 1800 megahertz uplink is a very cost-effective solution for 5-link uplink challenges. Our portfolio consists of tower-mounted amplifiers, single band and multiband, dual band and triple bands, and several other versions. Same band combiners, that is sometimes called diplexes, triplexes also. Sorry, same band combiners, that is my mistake. Same band combiners when we add two systems in the same band. Multiband combiners, that is what we often call diplexes, triplexes, pentaplexes, etc. We also have a broad range of interference rejection filters that is needed for collocation of many systems. We also have PIM test and measurement systems, because in this webinar we've talked a lot about the uplink, and PIM is and will even more so be one of the major limitations to uplink performance. And PIM is the best way to reduce PIM is to make sure that you never install a rotten egg in your site. So do PIM testing of all your incoming goods before you install it. So make sure to have a good PIM tester in-house. And you can contact us in any of our sales offices around the world, or follow us on Facebook or LinkedIn. Thank you very much for your patience, and hope to see you someday in a face-to-face situation. Bye.